let's go through an example where we are breaking the rules. So we talked a little bit on Monday about breaking octet. So there are some exceptions when we're dealing with the octet rule. We like to assume that everything gets 8 things around it and everything works out nice and neat. But like we've covered in Chapter 6 and Chapter 7 with trends, while in general this rule works most of the time, it doesn't work all the time. For the octet rule, we sometimes see this octet rule breaking in elements or atoms in the end of 3 shell, so in the third period, when we have negative or not negative odd numbers electrons and things like that. So if you look at phosphorus pentachloride, we see that typically we would expect phosphorus, which is in the group 5, to have 3 bonds around it. But you see that phosphorus is in, if you look at the periodic table, is in the 3rd row. And so it's a fairly big atom. What that means is that it can fit more bonds around it. So if you look at obeying all the rules or all the lists that we talked about, the first thing, no matter what you're dealing with, is calculating total valence electrons. Here we see that phosphorus is in group 5. There's 1 of them. Sorry, so you have 5 electrons from that. You have 5 chlorine atoms. Each chlorine is from group 7, so you have 7 valence electrons. So you have a total of 40 valence electrons that you must account for. Just like before, you put all the players on the board. So you have 1 phosphorus, 5 chlorines. Phosphorus will bond to all 5 chlorines. Okay, so through the bonding, you have 2, 4, 6, 8, 10 electrons from bonds. Yes, phosphorus has already broken the octet rule. There are 10 electrons around phosphorus, but that's okay because phosphorus is fairly big and it can handle it. Just like before, we see that you want to place the electrons all around the chlorine atoms, and for time, I'm not going to do all those dots. You see me do it in before. But we can see that for group 7 elements, no matter if you have fluorine, chlorine, bromine, or iodine, you should have 2, 4, 6 valence electrons. Its electrons and its octets should not be broken. So you see 2, 4, 6, 8 electrons around the outer shell. It can expand, so phosphorus can expand its shell to take in all these extra bonds. Because if you remember from chapter 6 when we talked about the shells, and you have the inner shell and n equals 1, n equals 2, n equals 3. So as you increase the shell, you increase the size of the atom. Yeah. Now with acids, that's another exception to our system. So here we don't want to put hydrogen as our central atom. Okay? We do know that because hydrogen can only bond once. Okay? So if we look at the valence electrons of all our elements, you see sulfur and oxygen are both in group 6. Okay? So you have 6 electrons from sulfur and then 6 times 4 from the 4 oxygens. And you have 2 electrons from the 2 hydrogens, totaling 32. So in this case, it's kind of hard to see where our central atom is because sulfur and oxygen are both in the same group. But 2 things. Notice, if you just look at the polyatomic ion of sulfate, you see that sulfur is first. Okay. If we look at the oxidation state of sulfur, it has a positive charge while oxygen has a negative. So we still obey the rules where the cation goes first. Additionally, you see that there are, while there is one sulfur atom, there are 4 oxygen atoms. That kind of indicates to, or that should indicate to you too, that there's only one sulfur, 4 oxygens. Where's those sulfur, or where are those oxygens going to bond to? It's not going to bond to the hydrogen because we know for sure that it only bonds once. So it has to bond to the sulfur. So sulfur is our central atom. So we put the 4 oxygens around the sulfur, okay, because this is our polyatomic ion. So no matter whether there's hydrogens or sodiums or whatever kind of sulfate you have, look at the polyatomic ion as its individual shape and skeletal structure. Okay, so in this case we have 2 hydrogens, but we've seen before with it could be a salt, and then that's a little bit different, but in this case we have our polyatomic ion, sulfur SO4, okay, and then the hydrogens have to bond to the oxygens, okay, because sulfur has its 4 oxygens around it. It's not going to bond to the sulfur. So hydrogens get to the outer oxygens. And while technically it doesn't, at this point, it shouldn't matter where you put the hydrogens, we want to treat it kind of like we've done before, where we want to space them out so that they're the furthest away from each other. So in this case, we've got rid of 2, 4, 6, 8, 10, 12 electrons through bonding. Okay. Again, it doesn't have to be just the bonds in the central atom. It's the total number of bonds in your whole structure. We still have 20 electrons to get rid of. Hydrogen, if you look at hydrogen, hydrogen has 2 electrons around this hydrogen, 2 electrons around this hydrogen. So its octet, you can't really see me, but I'm doing in quotation marks, octet, is complete. So hydrogen has its noble gas configuration. It is fine. So those 20 electrons must go around the oxygens. Okay. So again, for time, I'm not going to show you how to put the dots in, 2, 4, 6, and this is what we'll see. Now, notice a few things. Okay. This oxygen has 8 electrons, and so does this oxygen. But remember to look at the bond orders. Oxygen wants to bond how many times? 2. So you can see that this oxygen is happy. It has 1, 2 bonds. This oxygen only has 1 bond. Now we're not going to add any more atoms together, so that means we have to play around with where those electrons are going to go. Okay, so while we have accounted for all the electrons, okay, the bonds are not correct. Okay. Hydrogen wants to bond once, that's fine. Oxygen wants to bond twice, and there are 2 of those oxygens that are not happy. They're only bonded once, so we have to satisfy all bonding orders. Now, if you look at the location of sulfur, it, just like we saw with phosphorus, is in the n equals 3, so the 3rd period. Okay, that means it can expand its shell. So it has empty orbitals that can accept more electrons, just like phosphorus. It's bigger, it can accept more electrons, so it doesn't get stuck with its bonds of, in this case it should be 2, but you already expanded to 4, right? So let's just add a few more. Let's try to make the oxygens happy. And so what you'll see is we can take 2 of these electrons, okay, move them to form a bond. We could take 2 of these electrons and move them to form a bond. So sulfur has 2, 4, 6, 8, 10, 12 electrons around it. So 1, 2, 3, 4, 5, 6 bonds. Okay. And it's fine with that. It's fine because oxygen is a little bit more needy. Okay. It's not as flexible as sulfur. It can't expand its shells. It just wants 2 bonds. Okay. Sulfur has that flexibility. It is bigger, it has empty orbitals it can expand to, so it can expand its octet. So the takeaway message is start, no matter what you have, you start with counting your valence electrons. Okay, you bond everything together. Then you look at, are the atoms happy? Are they bonded the amount of times they want to be bonded to? Do they have their octet? Can we rule break? Can we break the rules for the octet if something like oxygens and hydrogens and carbons aren't happy? Okay. The thing to look out for is knowing which atoms can rule break. Okay, so if we have, again, refer back from Monday's lecture, if you're in period 3, if you have an odd number of electrons, things like that, there are rule breakers. Okay? Be able to identify when to break the rules. One of the key things to note is with phosphorus pentachloride and with sulfuric acid, or in this case hydrogen sulfate, is you can already see that sulfur has more bonds than it wants, right? It has the electrons it needs, it has the octet, but sulfur only wants to bond twice. Okay, it's in the same column as oxygen, so you already see that it's bonded more times than expected, so it's probably going to break the rules even further. Okay, with the phosphorus pentachloride, you already saw that, again, phosphorus is bonded way more than expected. Okay, and that's fine because both phosphorus and sulfur are in the third period. Now, if we look at this structure, okay, we can note a couple different things. One, why did I choose this way? Why did I say that these oxygens will double bond and these oxygens not? Could it go the other way? Yeah. So these are just suggestions. We don't know exactly how things are bonded. Okay. This is my prediction. We can say and argue that this structure is more stable because oxygen is bonded twice. But how do we actually know? Well, we have experimental evidence. So in this case, the bond length from X-ray data, X-ray is not just used for finding broken bones. It's also used in chemistry to calculate bond length and behavior of electrons. Okay, we can measure the bond length, so the distance between this sulfur and this oxygen. We talked a little bit about this when we defined bonds in chapter 2, I think it was. Okay. So if we just look at the sulfur and oxygen, okay, the sulfur oxygens are shorter between the oxygens without the hydrogen. Okay, and we'll see this nice table, but the length of the bonds are going to decrease as you have more and more bonding. So experimental evidence and just even theory supports that there are sulfurs with two oxygens. Sorry, sulfur with these two oxygens will be double bonded. Now you're not going to go and collect experimental evidence on all your Lewis structures. So there is a different way of doing this. Okay? So again, we don't want to perform experiments every time we want to verify. What we can use is formal charges. So again, just like the oxidation number, this is the apparent charge on the atom, not necessarily the charge. Okay, this is the charge an atom would have in a molecule if the bonding of electron pairs were shared evenly. Okay, this is a bookkeeping method. Again, I'm repeating myself, but does not represent real charges. And the sum of the formal charges on the atoms must equal to the overall charge on the ion or molecule. And we'll go over calculations in the next video.